So many thanks to Orgo for the invitation. So this will, I understand this is a very general audience, so it will be a very general talk. So please stop me when I start boarding you. Okay. So let me know when to stop basically. Okay. All right. So I'll be discussing some. I'll start with some history about this Brownian motion, and then this I will mainly motivate. So Brownian motion nowadays appears in many important physical models as well as in mathematical finance. And of course, it's an important object of study in stochastic processes in the probability theory. What I'm going to do today is to give a motivation of Brownian motion as the model or a model of a movement of a particle within a medium. So I'll clarify what exactly I mean. Okay, so our story. So I'll start with some bit of history. So our story starts in 1827. So there are nowadays there are further confirmations coming that maybe somebody else observed something much earlier, but we'll stick to this. This is the more official version, quote unquote official version. So there was this British botanist, Robert Brown. So I hope you can read my handwriting. Okay, great. Yeah, so what he was doing is that at that time he was interested in some specific type of flower pollens. These are very small things. So what he was doing is that he was putting them in a petri dish and looking at under the microscope to look at some structures and all that. So what he observed, so I'll draw something and then hopefully the meaning will be understood. So just think of this as your container. So there was some small layer of water, and let's say the particle, the flower pollen that he was observing, that's there. Okay? So it's submerged inside. So what he observed was that this was moving erratically inside the medium. So this was some kind of very surprising at that time. So there was no external forcing as such. It was not being shaped or any such thing. But the thing was moving around. So the main point is beyond like gravitational force. We are not really sure why there is some additional force is coming in. Okay. So now at that time he was unable to explain it. But what he did is what scientists do. Even if you cannot explain it, report it to a journal. So in the next year, immediately next year, it got published in some journal. So it caught attention to the scientific community gradually. The idea was that you see nowadays all this science are like pretty spread out, and we are all specialists. So at that time itself, there were people who used to dabble in like maths, physics, chemistry, everything, right? So anyway, so the question was that how do you explain such a motion of such a thing? Okay, so I'll move on a bit more. So from these like 1820s, 1830s, let's move to the mid 19th century. So mid 19th century is around 1850s, 1860s, around this time. So now many big names came in and gave multiple theories. Some got invalidated, some got validated, and how things progressed. Okay, so I'll recall two names. So these two people are usually cited for the initial understanding of what we now understand as atoms and molecules. Okay, of course we have a much better understanding, but at that time you have to understand that they didn't have much of the scientific apparatuses that we have today. But they came up with certain theories, and we now have a better idea of exactly what these atoms and molecules are. Okay, and gradually at that time itself, what we come to understand as heat, which is essentially connected to the nature of or the status of the matter. So presently we purely focus on three types of matter, the three stages like liquid, gas. So gas is on one end, liquid somewhere in between, and then solid. So these are so there are other extremes, but we typically focus on this. And the idea is that this matter has these three stages, and this is directly linked to the internal kinetic energy of the molecules there. Okay. And so the heat or the temperature, whatever you want to call it, it's essentially a representation of the stage of matter. Right? So, and the main idea is that in a let's say liquid or in gas, you have much more energetic particles which are moving around with much more, with more kinetic energy.
Recording in progress.
Okay. So, with that, gradually, the explanation that came up for these motions, I will draw that again. So, you see this flower pollen that I am talking about, it's very, very small. Okay. So, the idea was that the water molecules that were there in this medium, they were moving around with their own kinetic energy with certain directions and all that. And at every instant, there was some collisions happening. With the water molecules were hitting that whatever particle that we were looking at. And since they were moving in different directions, different velocities and all that, there is a resultant, after the every instantaneous collision, you have a resultant force that made this thing move to a new location. Okay, and immediately, of course, in the next instance, it's still surrounded by other water molecules. They were again bombarding it, and it's forced to move at a different location. So that leads to the actual erratic motion that we see. So this kind of became the understanding in around 70s, 1880s, 1870s, around that time. And then, so once this came up, then the formulation of this mathematical formulation, all of that was discussed. So now physicists as well as mathematicians jumped in, and many people had several contributions to it. And then, of course, in early 1900s and so on, immediately around that time, it also suddenly got used in some models in finance, and things started taking off. Okay. So I will not mention too much of the further history, because I want to go into a bit more into mathematics, but I will mention one important name. So this person, so everybody has heard of him. So in 1905, he wrote a very, very famous paper on relativity. Okay, of course, he has many other seminal contributions to the world of physics. But in 1905 itself, Einstein gave a very precise mathematical formulation behind this motion. Okay. So his interest was more coming from the thermodynamic situation. So thermodynamics is exactly that. You have heat, and you want to essentially explain the attached dynamics of certain system. Okay. All right. So so of course, at the same time, he was working on that relativity kind of thing, and along with that, he gave that some mathematical description of this. All right. So I won't go into the thermodynamics part. I am not at all an expert on that. But I will try to explain a bit more about my understanding of what is this motion. Okay. So so since Robert Brown officially quote unquote observed this, so in his honor, we recognize this as a Brownian motion. Okay, this kind of a motion. So the first thing is that I'll repeat again. What we are now doing is that we are dropping a particle, a very small particle, in a medium. The medium's molecules are in motion. They are having instantaneous collisions at every instant, and that makes things move, and we are just observing this resultant motion. Okay. But one important thing is, if you repeat the same thing, you would possibly see a different path that as it comes out. Okay. So what we are essentially interested in are the type of paths that come out in all these experiments. Okay. All the set of possible paths. So that whole thing as a whole we would refer to as the Brownian motion. Okay, so let's get into the mathematical formulation of it. Okay, so just think of it as a physical experiment. Okay, how do I record such a path? first of all, I should have a clock in my hand. So I start at time 0 and I start observing the location of the particle. But to be very, very precise, I should really fix some set of measurements, some way of measuring the things, right? So what we can usually do is that we forcefully bring in a coordinate system. So everything is happening in 3D, bring in the standard Cartesian coordinate system, and you keep recording the location of the particle. So you get a set of 3 coordinates. Simple. Okay? You just keep recording it. Okay. So overall, the way we are therefore modeling it is that you fix a time interval, that's the domain of the function, and then for every time point you are essentially getting a location in R3. Okay, and for simplicity, let's ignore the boundary of the container. It's as if the particle has some infinite freedom to move. So you see what happens is that if you start somewhere in between, the particle will move around and will reach the boundary after some stage, but till that time it's moving freely in some sense. Okay, so for the moment, just as a very simple model of motion, I am keeping the range as like unbounded in R3. Just as a very simple. Okay, but as I said, we are interested in the set of all possible paths. Okay, so as I want to clarify this part a bit, that if I drop the particle or start the motion at a certain instant, even if we are leaving the particle in every experiment at the same location, we possibly end up getting a different path, resultant path. So strictly speaking, this description that I have given for the possible path is not really complete. Let me clarify. What I want to mean is that it's not only just a function of time. So if it was just a function of time, we would have seen the same path over and over again. We don't see that. So somehow we have to add some additional extra variables that accounts for these various possibilities of paths. Okay. So what we do is that we remove this thing and make it a slightly more general model, and that's what we are going to work with. Okay, so let me clarify what exactly is happening here. I am bringing in an additional variable in the domain side. Okay, so typically what happens is that as soon as I start the experiment, what happens is that you essentially end up fixing a point in that first domain or the first set, which is essentially keeping track of a list of paths. Okay, so the omega naught that I am fixing, it's a single path that somehow got fixed. Okay, I'll clarify this in a moment. But suppose that gets fixed. Okay, then what happens is that as soon as this point gets fixed, it's therefore purely now is a function of time. Okay, so what you essentially keep on observing is this mapping that takes any time point small t to this number which is in R3, and this is what you record. You record the time and the location. We don't really have a formula for this. Okay, this is as a whole, this is just a symbol that denotes a vector in R3. So this is what you keep record. What you are recording is exactly this information, time and the location. Okay. Now let me come to this choice of omega naught business. Okay. So what typically happens is that, as I said, I have written this very important word about all possible paths. So the way we proceed here is that we understand that in the background certain probabilistic things are happening, and therefore this essentially accounts for all possibilities, and therefore what we would like to do is to bring in the structure of probability space there. Okay, so I am not going into the exact probabilistic model there, but what I will do is that I will say that there is a way of measuring things in that set. So typically that is done by bringing in a probability measure and considering some appropriate class of subsets which we call as a sigma fits. Okay, So for those who know about it, we bring in this structure, this triplet, and we work with it. Okay.
What is the meaning of path here?
Okay. So what I am simply saying is that this exact thing. So omega naught essentially represents this path for you. It's a function on time. So path is simply trajectory or a function of time.
From 0 to t.
Domain 0 to t to R3. That's the path. So we are interested in set of all possible such paths under such a mechanism. Okay. So let's try to figure out some properties of this, and that will actually end up giving us or leading us to some sort of a definition or the accepted definition of what is a Brownian motion. Okay. So let's start. Okay, so I'll now start writing down certain conditions and let's see if these are accepted. So first condition. You see, as soon as I said that this was essentially an experiment, I should standardize it. So one standardization was already bringing in that coordinate system and all that. But since we are essentially studying a motion, it would be ideal if we repeat this and start every time I start at the same location. Okay. So what we will do is that wherever we start, we should really think of it as the origin. Okay, this is just a matter of standardization. You could choose to start at other location, does not matter, but you can always shift your coordinate system and get back to the same location. Make it start at the origin. Okay. So what we will do is that we will say that no matter what path you are using, and but at time 0, you always start at this location. So 0, 0, 0 is that origin in R. Okay, this is just a matter of standardization. And so this we can ask for all possible paths that we have. Okay, but in practice we make it. So this is the layman's definition that for all paths we start at 0. But to be more mathematically precise, what we do is that we simply think of this as or maybe let me state it slightly differently. Okay, so this is good enough for usual understanding that so you can ignore something that is happening with probability 0, ignore such things, but everywhere else with full probability you would really start at 0. Okay, we now start treating it also as a function of omega. As soon as now you have fixed the initial time point, it's only the function of omega, and in that variable we say that all possible things we are essentially starting at the origin. So this is not a big thing to ask. So that's our first condition. So let's bring in the second condition. Okay, so the pictures that I had drawn to you, so the particle was moving erratically, but you see so this is now more, so yeah, now philosophical stuff. So we had drawn the path without lifting the chalk from the board, right? So that was one of our very layman's definition of what should be a continuous function, right? So that's exactly what happens. So we observed that kind of paths in practice, and therefore it's reasonable to ask that whatever paths we see here, they are continuous in the time variable. Okay. So again, I'll put in a layman's definition, then a probabilistic definition. So what we will like to say is that for all omega, okay, and so this is the layman's definition, and the more probabilistic definition is that so that's what is typically referred to as the continuous path property of random motion. Okay, so we start at location 0 and we see continuous paths. Okay, so far okay. I mean, yeah, please.
Physically, all paths seems like all paths should be continuous. So How can a particle just?
Yeah, there can be jumps.
I see.
There can be jumps. If there is a very catastrophic event, you would see jumps. So far, no catastrophe is happening. Everything is simple. Okay. So you see very two simple conditions. Now I'll bring in something more. Now the main thing start. So I'll bring in another condition in. So let's do it here. So again, I am discussing properties of this thing so far, right? So one, just to reduce the amount of analysis that you have to do, one simple thing would be to consider a further projection. So let's say I just look at the first coordinate thing. Let's make life even simpler. I have 3 coordinates I am recording each time, but for the moment, let's start simple. I look at only the first coordinate. Okay, so I project it down to the first coordinate. So that's what I am going to look at. And again, without including too much notational complexity, I will just try to think of it as, I will write it as B again. So I am now thinking of that path in the real line, the first coordinate I am looking at. I am just looking at the thing. So whenever I am writing it down, it's for the one-dimensional motion. Okay. Okay. So for that, so let's bring in some further physical. So this is our medium, and here things are moving. Now let's actually draw it bigger so that. Okay. So here, let's see. So let's say I have started here, and this is what has been exhibited. Now you fix 2 time points. So let's say this is S, this is T, and I would like to look at the displacement. Okay. So if you were in the 3-dimensional situation, formally that displacement would be something like this. So I would now start suppressing the omega, because essentially I am trying to look for something happening with full probability kind of thing. So I will treat it as a function in omega. So that's why I am writing a dot, but I will keep writing the time variable here. So if I was still working in the 3 dimensions, this would be a vector in 3 dimensions. So that essentially records the displacement or the increment, right? And if you are in the 1 dimension, if you are projected down to 1 dimension, you are just looking at the increment in the first coordinate. That's all, okay? Alright, but you see why this increment has occurred. It has occurred due to this continuous sets of collisions, as I have explained to you, okay? So what we therefore would like to make a condition or make a statement about that why this displacement has occurred. I will repeat, it is due to the collisions that happened within this time interval S to T. Simple. But you see, we started at time 0 and we also had to move to this position at time S. That happened due to the collisions that started happening from time 0 onwards to time S, right? So that ensured the displacement from location 0 to location whatever this was, and then the further displacements from time S to time T, this displacement happened due to the collisions within the time interval only. So if you say that the initial set of collisions that happened, they seem somewhat not related to whatever collisions I see afterwards, meaning within the new time interval S to T, then I can posit that the original displacement that was there, that should have in some sense no relation with the displacement that happened now. Okay. So let's write down the 2 displacements that I am talking about. First is of course, so I will start suppressing the omega also, so that I was writing so far. I will start suppressing it. I will focus only on the time variable now. So this is the initial displacement that I had up to time S. Okay. And then the second displacement that I was talking about is this. These displacements are happening due to a set of collisions that happened in the first time interval 0 to S, and then I had another time interval S to T, and that led to the second displacement. Okay. So it is reasonable to now make a statement that as random variables, there is a hidden omega that I have, as random variable this should be independent. Okay, and that leads to the third condition, which is called the independent increment property. Which says that you choose such finitely many time points and then you make a list of these displacements. So first is of course T1 minus T0. So of course you see T0 or 0 that I was writing here, as per our first condition, that's the origin. Okay, so strictly speaking I could directly write it as B within bracket S. I mean this is just 0 again, but I'm just writing it for no, so that there is no confusion. So this is a very important condition. It's called the independent increments property for the Brownian paths. Okay. All right.
This is for all partitions?
This is for
All partitions of 0t or just?
so yeah. So for all n greater than 1 and for all choices of t1 to tn, you should see this, because that's what we kind of observe and put it as a thought. Okay, but okay, so let's again come back to this increments business. Okay, you see now this is where I am now going to bring in a bit more technical conditions on the physics of that motion. Okay, so far exactly what I have been discussing to you, what I have been explaining to you was this. So let me clarify this with slightly more technical terms. So this is exactly what we have been discussing. So this is the So I have been discussing to you the motion of a particle in a homogeneous medium and with no external forcing. So I was not shaking the petri dish head on. Okay. Now let me clarify what exactly this homogeneity means. It's simple. All I am saying is that the medium that I have, that was water in our case, from different location to location, there is no change in density, pressure, temperature, and all these things. Okay. And the example of heterogeneity would be, let's say you could in a glass you could put oil and water and they would essentially separate out, and that could be one possibility. Or for the external forcing you have to go to, let's say, a river or a sea where there are tides and all that. That would give you some external forcing coming in. Okay. Of course, in a sea, there is with depth you would see change of pressure, so it's not homogeneous in that sense. So all those things will come. Okay. So now, of course, the simple motion that we are discussing, it's in homogeneous medium with no external forcing. So of course, as soon as I complete the definition, the immediate question will come that how can you go to heterogeneity and include external forcing, right? So that's so okay. So let's complete this definition and then we'll try to go there if time permits. Alright, so let's see. So here, what the role of homogeneity is this. So let's go back to this picture again. So let's just draw one such. So it's a very erratic motion. So now you, let's say, initially this was the location, and look at a very small neighborhood around the particle. So you see that if I was in that particle's position, what I would, if I look around, I would see a dense mass of water particles, right? Water molecules. They are moving around. But then, if I were to move to a new location and again look around, again I would see again another bunch of water molecules, but due to the homogeneity, what we are essentially specifying is that these neighborhoods look the same. And the water molecules and everything, whatever with distribution, they are moving around, but overall their distribution of like kinetic energy and all that, or the velocities that I see, overall distribution, I'm not talking about a single water molecule, but as a whole, they look the same. That's what is the role of homogeneity here. Okay? Alright, so I move around and all the things look the same. So my behavior of, or the movement that I see, the resultant displacement that I see, roughly is somewhat, should be similar. Okay, so I want to formulate that as a condition. So what we would like to say is that, you see there is a continuous set of collisions happening at every instant. And as I move around, I see this kind of a displacement happening from time s to time t. But overall, what it really matters is the length of the time interval rather than where you started. Okay? So you see in this time interval s to t, the start time is s, end time is t. You spend the time t minus s unit of time, and in that you have got some displacement. That displacement essentially depends through the length of the time interval, because overall at every instant that you essentially have this continuous set of movements, they lead to as a whole this displacement, and overall that's how the behavior should look like. So what we formulate as a fourth condition, so let me write here. So this is called stationary increments. And what it says is that if you look at the distribution of Pt minus Bs, so I should write the distribution of, so when I say the distribution, I mean the probability distribution of this specific random variable depends on S and T through the exact values of T and S does not really matter as long as you know T minus S, the length of the time. Okay? Alright, so we could go on and start writing down more properties, but let's start somewhere. Okay? What does it lead to? Okay, so let's now do some, so far I have been discussing some history and then some physical mechanism, so let's do some mathematics. Okay, so how much time do I have?
30 minutes.
30 minutes, okay. So hopefully I'll tell you, I hope I'll be able to tell you some mathematics about it. Okay, so alright, so for now, this first condition that I had written down, that was still in 3 dimensions. Okay, but then somewhere in between I changed to the looking at the first coordinate. But just to clarify, what we end up observing is that even if you look at one coordinate at a time, the behavior remains the same. Meaning, and they don't interfere. In the sense that if you look at only the first coordinate, whatever nature of displacements that you see, it would behave in exactly satisfying these 3 conditions. If you were to look at the second coordinate, you would again see this continuity, independent increments and stationarity. And the 2 motions, again that can be described that these 2 motions, the motion in the first coordinate measurement or the displacements, they behave exactly in the same way as the second coordinate. Okay, so essentially if you can discuss the one-dimensional motions, due to the independent nature, you can essentially lift it to higher dimensions. So that's essentially the idea. Okay, so yeah, please.
So we can take a R3 value random variable.
Yeah, we can, of course. But all we are saying is that if you just look at the first coordinate of your random vector and the second coordinate of your random vector, both are now random variables. As random variables, their distributions are independent. So you can build up the distributions just by factorization, standard. And that reduces the nature of the analysis from R3 to R. So we want to make it simple, as simple as possible. Okay? So we'll see how to bring in so at least in this motion, things will be not linked, but we'll see when we bring in this heterogeneity and all that, that's where there will be some interlinked between these things. So there will be dependent structures coming in. Okay. So, so for the moment, what I am now discussing is purely in the one-dimensional structure. So, all right. So, if you read about the standard definition of a Brownian motion, you would see these properties only, except one very important omission. Okay. So, you will typically see this additional stuff. You will typically see that the exact distribution is Gaussian or normal with mean 0 and variance t minus s. Okay. So this is what we typically read if you just pick up a standard textbook and you will see this.
So you mean this is one of the assumptions, or this you get out of from 1 to 3?
All I am saying, that's what I would like to lead to, that these 4 conditions that I have told you essentially leads to this, and therefore in standard textbook you would see that as part of the definition. I would like to give a purely heuristical clarification about why that should be so. Okay, and this connects to something very important in probability theory, a very important result called the central limit theorem. Okay, that the nature of this random variable should be Gaussian. Okay, so let me take up a few minutes on that. Okay,
that first condition comes under the definition of Brownian motion, or it is an assumption?
The first condition, it's essentially, as I said, so you can start your motion at any point. So there are more general definitions of Brownian motion. Here you say you start at a location x, that you can always do. Okay. But you have to start at a fixed point. That's important. But for simplicity, I start at the origin. So this is what is typically also referred to as the standard Brownian motion, because starting at origin. You can always shift and you would see the similar behavior or similar nature of the motion. But everything now gets shifted by that x. It's just attached to the shift of the coordinate system, nothing else. Okay. Alright, so let's see. Okay, so as I said, there was this independent increment property which tells me that if I take 2 time points like this, then if I look at this random variable, this is what a very simplified particular case of the independent increment property. This is what I motivated anyway. So now here what you can also say is that if you, I think I erased that motion, but what has been shown is that the fluctuations that you see there, if you try to do a some specific measurements and do some analysis on the nature of average behavior and second order fluctuations and so on, which essentially leads to these random variables mean and variance, physically you can justify from the physical measurements that you can justify that this should be finite. Okay, so when we are doing our analysis, we will assume that the motions that we are analyzing or the random variables that we are analyzing has up to second moments. Okay, so mean and variance exist, so I can do some calculations. So this is purely again coming from the physical experiments, and as a consequence of this, what you can now do is that you can write, you can do this interesting set of computations. So I have added and subtracted the same quantity here. Okay, but now you see this first part that I have highlighted is independent of the second part, and this is a very simple property of the variance that now due to independence variance will add up. Okay. Okay, so far so good, nothing major, not too heavy mathematics. Okay. But now, so far what I have used is the third property, independent increments property. Now comes the role of the fourth property, the stationary increment property. You see the first part that I see here, it's Bt minus Bs. Okay. Now I say that since the distribution of Bt minus Bs only depends on T minus S, and variance essentially depends on the underlying probability distributions rather than the actual random variables that I see, I should be able to write it as yes, because this random variable has the same distribution as this one, and therefore their variances should be same. This is how I have used the fourth property. So the first one was the independent increments property, and here I have used the stationary increments property. So overall, let's look at this kind of a mapping. I could ideally this is. So take f of e. So let's say I declare this function. I don't want to keep on writing variance of Bt, variance of Bt. What I am saying is that this function satisfies this very interesting functional equation. So if you pick up any two time points now, T and S, variance adds up. So that's what I have essentially written. Okay? So this is the structure of the variance. Now with some very mild assumptions, which can be again verified from the experiments and all that. Okay, so let me give you a quick motivation also for this. So again, I was doing the experiment up to some time capital T, but if I could go on and do it on 0 infinity, for example. If this function were to be continuous, it's a very standard argument that says it must be some constant multiple of t, right? And you don't really require continuity, you require some very mild assumptions, even lower than measurability. Even under that, you can get to the same solution of the functional equation now. So what we are saying is that we are looking for functions that satisfy such a property. Okay, so function is the unknown is the function is the unknown. This is typically called functional equation. So and this one is specifically called the Cauchy's functional equation. There is a huge literature on it. So for example, you could bring in other operations like f of t plus s going to the multiplication of these two numbers. I have used additive here, but I could bring in multiplication, or you could have multiplication here and get the ask for the addition here and so on. Okay, and these very interesting things come up. So for example, the last one that I told you about, f of t times s equals to ft plus fs, that is satisfied typically by logarithmic functions. Okay, and the other one where addition goes to multiplication is satisfied by exponential functions. So like these are all functional equations and lead to certain class of functions. But okay, so we are specifically interested in this, and as I said, with some mild assumptions, you can show that your so now I'll so f of t was variance of Bt. So let's write that explicitly because I am interested in the growth of the variance. So this is the output. Just using independent increments and stationary increments property, that it must be exactly of this type. Okay. Alright. But you see, suddenly a constant came in. So this is purely an existence result, right? And suddenly there is a constant. So what is the meaning of this? Okay. So again, see, all we have is the experiment. So we have to go back to the experiment and try to give you justification behind this constant. Okay. You see, what we are essentially measuring is, so B of t you should think of as the first displacement from origin to the time t. Okay, that is the nature of the displacement that you are seeing, and we are saying that that second order fluctuation, which is captured by the variance, is of order t with some constant hanging around. Okay, so what is this constant? So let's go back to this. So there is a coordinate system that I have used in my measurement. what exactly is happening is that you see, as soon as you have taken a coordinate system, there is a standard unit of measurement, what we say as 1 unit, right? Now, let's say that could be your centimeters, inches, and all that, and therefore the displacements that you are measuring, those are in that unit. Okay, so if you change the nature of the unit, the variance gets affected. Okay, so that constant is actually just coming from the coordinate system. So if you update your coordinate system, the unit of measurement accordingly, you can as well choose that constant to be 1. Okay, this is purely coming from the unit of measurement, nothing else. It's not really related to the experiment. You can update it, make it to be 1. So subsequently I will assume that to be 1. So that's why we say variance of Brownian motion is T. Alright? Okay, so that talks about the second order fluctuation, but now what about the average fluctuation? You see the same picture, let's go back to it. As I said, there is this nature of collisions and all this. So you see, let's say at this point here, the particles suddenly started moving down. So maybe overall, the nature of collisions that were happening around that time was that all the collisions were forcing it downwards, right? Now, you see, according to the homogeneous medium business that we discussed, it's also equally likely that we could see the same nature but exactly opposite, exactly symmetric in nature. So if this is a viable path, I would see the reflection of this also as a possible viable path. Okay, so overall, if you get a path that makes you move upwards somewhere at a time t, you would see also a possible viable path again makes you move downwards exactly in the same way, exactly in the same downward distance, exactly in the same nature, just exact mirror of the original path. Okay, so this is simply just by the homogeneity and all that. Okay, so therefore whatever probability whatever probability the particle is moving upwards, with the similar probability, exactly the symmetric nature, it will move downwards. So you would see positive and negative values with equal probability. That's the nature of symmetry, and essentially that translates into okay. So average behavior is 0 and second order fluctuation is T. This is taken. Alright. So let me now quickly give you the motivation why this random variable should be Gaussian. Okay. See, the mean zero business we have already explained. Variance T minus S is also clear because T minus Bs, as I said, it's equal in distribution with B of T minus S, and that has variance as per our understanding of T minus S. So I've identified the mean and variance. Only the distribution has to be identified. So that's what I'm going to do now. Okay, so for simplicity, let's take time 1. Okay, I would like to show that this is Gaussian. Okay, and I would like to show it. Yeah.
Functional central theorem?
No functional center limit. No functional center limit. So, okay, as I said, this is exactly same as this. Okay, because B0 is 0. I have done nothing, I have just subtracted 0. Alright, but now let's make life a bit complicated maybe. So I bring in some telescopic sums. Okay, so I add and so I essentially what I am doing is then I fix a large natural number n. I look at the interval 0 to 1, just subdivide it with equal length subintervals of length 1 by n. Okay, these are the endpoints, and I am simply looking at the increments that are happening in that each individual subintervals. So I add it up, I get this. So far so good, no problems. Alright, but so far all these were exact equalities. Now you see, let's look at the nature of the each separate displacement. This, I will write this to denote equality in distribution, not exact equalities. This has the same distribution as something like this. Okay? And how many such things you have? You have n many. Okay? So I have n, and moreover these individual subintervals that I have picked up, they are disjoint, and I now use the independent increment property. Again, I say that this is the sum of n independent copies of this random variable. Okay? So overall, I am saying that my B1 is equal in distribution with, I will write this, but hopefully the meaning will be clear. So I am not saying take one generation of B of 1 over n and repeat it. I am saying you generate it separately, n independently, and look at this. Okay? So this is n independent copies. Okay, so far so good. I have just used, again, going back to the basic properties only. Okay, so let's see, I think this can be moved. Okay, but I will do some slight jugglery now. Okay, so this was probabilistic. Now I will do some more algebra. Okay, so what I do is that I write that summation again once more. That's the summation. I have done nothing. Again, I will do essentially nothing. I subtract out the mean, but I know the mean is 0. I really do nothing. Okay. Now, what I am now trying to do is related to what is typically called normalization or standardization of a random variable. That you subtract out the mean and divide by the square root of the variance. So that overall the new random variable that you end up having, that will have mean 0, variance 1. That's what I am doing. So there will be hopefully some scaling factors, but let's see what the scaling factor is. So what I am supposed to divide by is the square root of the variance of this quantity. So let's write that down. Yeah, hopefully the brackets are fine. No extra brackets, hopefully. Okay, so I have divided by the square root of the variance. So since I am writing an equality from the previous step, I would ideally multiply by the same amount and make sure everything is fine, right? So before I write that down, let's just simplify what that variance is. Okay? So it's as I said, it's the n independent copies are there. So it would be n times the variance of yes, variance adds up. Same thing I am using. Okay, but what did I agree? So what did we agree that variance of bt is now t. So here it's 1 by n. So this is. So I don't have to do anything. Okay, so the earlier expression is exactly the same as this expression. Already standardized. Okay, so what do we have? P1 is equal in distribution with a sum of n independent random variables, but which has already been standardized or normalized. This is true for all n. And so here at every stage n, you have equal distribution or same in distribution. This is formally, now this is a heuristic argument that connects to the central limit theorem that says this must be Gaussian if this keeps happening for all n. Okay, that's why this B1 must be Gaussian or normal. Okay, and we have already identified the mean and variance, so that doesn't. Okay, and I could as well have taken a general time point t, subdivided into this n length partition and ran the same argument. I would exactly end up with this. But there I would have to be careful about the computation of the variance. Some scaling factors would come. Something with t and all that. That's where the variance comes. That's it. So now we are therefore in the stationary increments property we can as well say that bt minus bs, the distribution of it is exactly normal 0 t minus s and be done with it. Okay, so that's the typical definition of Brownian motion that will, if you pick up a standard textbook, you will see this. Okay, but it comes from this motivation. Okay, okay. So how much time do I have now?
7 8 minutes.
Okay, so I'll quickly give you the heterogeneity and maybe stop. Okay, I'll not talk about any of my results. I'll just quickly discuss the heterogeneity part and I'll finish with that. Okay. So maybe this one. So now motion. Okay, so again, I still continue with no external forcing. I'll bring that in again finally. Okay, so let's try to see if we can capture this heterogeneity and what is the effect of the motion there. So the first thing is that the homogeneity played an important role in the stationary increments property, that all the neighborhoods were looking the same, that if you look at a particle at a specific location, the immediate neighborhood, water molecules, they were moving around with the same velocity and all that. Okay. In case of heterogeneity, that will not be the case anymore. Okay. All right. So however, you can still try to do the exact same thing we did here. Meaning, this is again a new experiment. You bring in a coordinate system, start at time at location 0 at time 0, all those business, write it as some function of time and all that, bring in the set of possible paths. So what I will do is that I will now, just to distinguish with the original Brownian motion, I will write it with a different English letter, that's all. Okay. So again, I would end up with something like this. Okay. So again, so right now I'll do it R3 directly. I think we have a reasonable understanding of what is one-dimensional Brownian motion, and then, as I said, the three-dimensional Brownian motion you can just look at as n independent copy, 3 independent component copies, each of which are one-dimensional Brownian. Okay, so with that understanding, I'm trying to make sense of this. Okay, so here again I start looking at those 4 properties. I think I erased a few. But again, I start at location 0. That should not be a big deal. Again, hopefully the nature of the explanations that I have given, again we should likely see continuous paths. So the original 2 conditions roughly remains the same. Now the 3rd and 4th property are related to the nature of the increments. So I am now interested in this. So I bring in 2 time points. And I am interested in the nature of this increment. Okay. And you see, the idea is that this increment is made up of again all these infinitesimal increments that I will have. Okay. So you bring in a very small time interval, as we do, t to t plus some delta t, a very small time interval. And there you try to look at the infinitesimal displacement that you will see. Okay. So what I will now do is that instead of looking at s and t generally, I am now looking at t and t plus delta t. So this is the notations I am going to use. So what is the displacement that I see for delta t? this just I am denoting by this delta of x3, that the displacement that I will see in that time interval. Okay. So you see this is in R3. That's the displacement, it's a vector in R3. Alright. Now let's try to see the physical event that was happening. So I am here somewhere at time t, and I see a small displacement, that's my delta x. So this is at time t, at t plus delta. Now here it's very important, what is the nature of the medium? Why? Because if it is a high density region, you would see more particles or more molecules in the neighborhood. There may be more collisions happening at a single instant. Okay, but very dense maybe in some sense, maybe also will say that you have less freedom to move about and you may have less kinetic energy. Okay, if it is very dense, then that would be likely the case. Okay, so overall, from neighborhood to neighborhood, from different locations, you would see different types of your fluctuations or the displacements, right? So that we would like to capture some, that it's essentially a local behavior that affects the motion. Originally, you would have seen the same fluctuation as Brownian motion, but it's essentially getting scaled in some sense by the local behavior. Okay, and here, as I said, we are exactly recording the location. At this location, so this is exactly the location x of t, right? So all I am saying is that exactly in that neighborhood of this point, there is some local information that affects the motion, and that makes it differ from the usual Brownian motion. Alright? So we make a very simplified model saying that the nature of the correction that is happening due to all this local behavior, it's multiplicative in this sense. So ideally you would have seen the Brownian displacement. All I am saying is that you factor in the local behavior and that you capture by a function. Okay, this is a very simple proposal, that you have a vector in R3, and to make this a proper vector matrix equation, you make this a matrix. That's your local behavior. Okay, it's exactly at that point there is some local information that makes it differ from a usual Brownian motion. This was the usual Brownian increment that you would have seen if everything was same. In that case, this function is just nothing but 1. You don't need to look at it. Otherwise, there is a local behavior that is coming in. Okay?
Same is 0 also.
Yeah. So it could be. So I'm just formulating the thing. Yes, it could be 0. All right. So now so I have just brought in a function, right? So let's be clear about the domain and range of this function sigma. So all I am saying is that as the argument I am placing in the present location, which is in R3. So it's a function from R3 to the 3 by 3 matrices. Okay. So sigma is a mapping like this, and this is typically called so this function it's called the diffusion coefficient, and so this is the infinitesimal form or the differential form of the equation, and you would like to it as formal differential equation, and so formally it would look like this. And this is what is typically called as stochastic differential equation. That's it. It's a motion of a particle in a heterogeneous medium. Alright. And then, so you would like to solve for the unknown capital XT, you would be given the initial condition and all that. Maybe you can start at location 0 as I said, but you could also choose to start at other locations. Okay. So there is a standard behavior given by the Brownian motion. In terms of that, you would like to solve for this. So Brownian motion is assumed to be given. The unknown is capital XT. And it could get determined as long as you supply this domain, the medium's information through this diffusion coefficient sigma. Okay. And so finally, let's bring in the external forcing bit. Okay, so it's not that complicated anymore. We are back to usual Newtonian mechanics. You have some external force. So again, in that small time interval t to t plus delta t, you would have a certain velocity. So with that velocity, you would velocity multiplied by this length of the time interval. That would be exactly the displacement due to that forcing. Correct. So this model that I was telling you about, the infinitesimal displacement, that would you just update it by saying that delta of xt so that's in some sense the velocity at that point. Again, that may depend on your local information, so I plug it in as a function of the location. Okay, because at that location there might be some local behavior that hinders or enables some movement. Okay, so all right, and maybe the forcing is different at location to location. So all that information is getting captured in that coefficient b. And again, let's as we have done here, let's match the dimensions. Okay.
Why can't we capture that extra thing here through this diffusion coefficient?
Okay. So that's this nature was purely due to the collision nature, and we are now adding the external forcing, that is the purely Newtonian mechanics. That we have forcing, so that leads to certain acceleration, gives you the velocity essentially, and you get the displacement is exactly velocity times that the amount of time window that you have. So the scale, okay, so this may be another point that you should highlight. The scale of this fluctuation, as I said, the variance was t, so the second order movement is t, so overall it behaves in root t scaling, whereas this is the usual linear scaling. So in another way, so let's say I take the delta t to be, let's say, something small, okay, small varies from person to person. Just for as an example, let's take 0.01. Okay. Now that is your delta t. But if you are to look at the square root of that, that's 0.1. That's higher in order. So square root actually in 0 to 1, the fluctuation in square root is much higher. Okay. So the usual Riemann integration scaling that we know about, it's dt. Okay, but we are now working in delta of square root as a delta of square root t, which has a higher order of fluctuations. That makes it different from usual classical or usual analysis or usual calculus. Okay, and that leads to what is typically called the stochastic calculus. We end up having some additional terms when we try to integrate things. Okay, so this nature is completely different. This fluctuation order is much higher in a small time unit. So that's what essentially also is reflected in that very erratic motion. Okay. So it's not differentiable. So those are certain properties that we see. If it was differentiable, you would have seen the usual t scaling.
What about this one? This is, you're assuming this to be continuous?
I'll come to that. So formally, I'm just making the equation. Then I'll say that. So nature of solution and some statements with existence and uniqueness of solution. I'll stop with that. Okay. So I have added this. So let's match the dimensions exactly as we have done here. So everything is happening in R3, all the terms. You see that time is one dimensional. So somehow the dimension has to come from these coefficients. So therefore it's natural to say that that's the correct dimension of the domain and the range. Okay, and this is typically called the drift coefficient. Okay, so taken together, the final model that we get is this. Okay, so this is the usually what is typically referred to as a stochastic differential equation. Now, I mean, the previous version there was no drift, but I have added the drift now. So this is the usual term. So again, but the presence of this first term is what makes things interesting. It has fluctuations of higher order fluctuations. Okay, and typically to talk about existence and uniqueness in this situation, you would have to somehow resort to notions of integrations, because typically these, as I said, these fluctuations are of very higher order and you don't see derivatives. Okay, so you cannot apply the usual ODE techniques to make sense of this. What you have to do, you have to essentially build up a new integration theory. That's called Ito integration or stochastic integration, and you make sense of these equations through the corresponding integral equation. So by that I mean that if you get your process satisfying something like this, so I am assuming for the moment zero initial condition. So otherwise you would add some initial condition, maybe let's say x naught where you start. Otherwise you would bring in something like this. So you try to, so given that you get a some integration theory which allows you to make sense of this term here. The other term is the usual level integration or Riemann integration, whatever it is, depending on the regularity of the coefficients and all that. But if you can make sense of this term that I have highlighted, then you get an integral equation in the unknown capital X as a function of t, and you would like to solve this. And typical results, a general class of results says that if you have Lifshitz coefficients, so sigma and b are Lifshitz functions, then you would get the solution. But there are further more general sufficient conditions ensuring existence and uniqueness. And again, the notion of solution also, as you might expect, as soon as you bring in a new theory, the exact nature of solution you can try to interpret it in various ways. So that also leads to certain probabilistic nature of solutions, something in distribution, which are also called weak solutions and all that. So I am not going into the exact detail of that, but typically the solutions that we mean are in some sense strong solution, meaning you give me initial condition, give me that Brownian motion, try to solve for it and all. Okay, that's typically called the strong solution in this setting. So in that setting, all I am saying is that if you have sigma and b both to be Lifshitz functions, then you get it. And there are other sets of sufficient conditions under which this works. Okay. But I think this is a good place to stop about this. So this whole thing is extension of the Brownian motion that started as a motion of a particle in a homogeneous medium, but that led to this more grand model of motion. Okay, I'll stop.